There is a star dying in slow motion above your head right now, and for the first time in human history, we have the tools to watch it happen in real time. And what we are seeing is not what anyone expected. For centuries, Betelgeuse sat in the winter sky as a dependable orange fire, the glowing right shoulder of the hunter Orion, familiar and constant, one of the few stars bright enough to hold its own against light pollution and city glow. But in the closing months of 2019, something happened that shook astronomers and amateur stargazers alike, something so dramatic and so unexpected that it rewrote entire chapters of stellar physics overnight. Betelgeuse began to vanish, not slowly, not subtly, but dramatically and decisively, dimming so severely that even people with no background in science, people who had never once thought about stars, looked up at Orion and felt instinctively that something was wrong. The shoulder of the hunter was going dark. Scientists scrambled, telescopes pivoted, the internet ignited with one singular question that spread across every platform and every corner of the world. Is this it? Is Betelgeuse about to explode? And now, years later, with the James Webb Space Telescope entering the conversation and viral headlines screaming that Webb has captured the star's final moments, the world is asking that question all over again with even greater urgency. But here is the thing that makes this story so much more extraordinary than any viral headline can contain. The truth behind what is happening to Betelgeuse is stranger, more layered, and more scientifically astonishing than a simple explosion. There is a hidden companion involved. There is a mystery that took decades to unravel. There is a telescope performing a kind of cosmic detective work that has never been done before. And there is a star that is, right now, experiencing one of the most violent and chaotic death spirals ever documented in the observable universe. To understand all of it, we have to start at the beginning. And the beginning requires you to truly grasp something that the human brain is simply not built to process intuitively: the sheer, staggering, almost offensive enormity of Betelgeuse itself. Most of us learn as children that the sun is big. We see the diagrams, we nod, we move on. But Betelgeuse is not big in the way the sun is big. Betelgeuse is big in a way that breaks the imagination when you sit with it long enough. If you were to reach into the solar system and swap our sun out for Betelgeuse, placing it at the exact center where our sun sits today, the star's surface would not stop at Mercury. It would not stop at Venus. It would swallow the Earth entirely, vaporize Mars without effort, and extend so far outward that its outer layers would stretch deep into the asteroid belt and potentially graze the orbit of Jupiter. The volume of this single star could contain billions of suns. Billions. And yet, despite this incomprehensible size, Betelgeuse is, by stellar standards, a teenager. It is only about 10 million years old. Our own sun is 4.5 billion years old and still in its prime. So why is Betelgeuse already falling apart so early? Because mass is destiny when it comes to stars. And Betelgeuse carries so much of it that its entire existence is lived in a kind of frenzy, burning through fuel at a rate that would make our own sun look miserly by comparison. Betelgeuse shines with the intensity of roughly 100,000 suns. It lives fast and it burns everything it has, and that means its lifespan is incomparably shorter than a smaller, more modest star like ours. Right now, deep inside the core of Betelgeuse, a desperate and increasingly futile arms race is playing out between gravity and pressure. For most of a star's life, these two forces are in perfect balance. The outward pressure created by nuclear fusion in the core pushes back exactly hard enough against the crushing inward pull of the star's own gravity to keep everything stable. But Betelgeuse has already exhausted the hydrogen that fueled it through its youth. It burned through all of that long ago. Now it is fusing helium into carbon, carbon into neon, neon into heavier elements still, working its way through the periodic table like a gambler making increasingly desperate bets with whatever chips remain. Each new fuel source buys a little more time, extends the reprieve a little longer, but every transition brings the star closer to a catastrophic and irreversible endpoint. That endpoint has a name, and it is iron. When the core of Betelgeuse becomes dominated by iron, the entire game changes in an instant. Every other element, when fused, releases energy. Iron does not. Fusing iron actually requires energy rather than releasing it. The moment that iron core reaches a critical mass, the outward pressure that has held this monstrous star together for 10 million years will vanish as if a switch has been thrown. Gravity, which has been straining against this pressure for millions of years, will win in an instant. The core will collapse so rapidly that the word collapse does not quite capture it. In less than a second, a core roughly the size of Earth will compress down into an object just 20 kilometers across, a neutron star of unimaginable density. The shockwave from this implosion will reverse and tear outward through the star at a fraction of the speed of light, and Betelgeuse will explode in a Type II supernova, releasing more energy in that single event than our Sun will emit across its entire 10 billion year lifespan. This is not speculation. It is not a dramatic exaggeration for the sake of storytelling. It is a guarantee written into the laws of physics, as certain as any fact science has ever established. The only unknown is the timing, and it could be tonight, it could be 100,000 years from now. Astronomers genuinely cannot pinpoint it more precisely than that. This uncertainty, this feeling of holding your breath indefinitely, is part of what makes Betelgeuse so captivating. And it is precisely this tension that made what happened in 2019 so electrifying. When the dimming began in late 2019, the astronomical community did not ignore it or quietly file it away. Every major observatory in the world shifted attention toward Orion. Data poured in from ground-based telescopes, from space instruments, from amateur astronomers contributing photometry measurements from their own backyards. The scale of what was being observed was undeniable. Betelgeuse had lost more than 2/3 of its visible brightness. That is not a minor fluctuation, that is the star effectively pulling a curtain partly across itself. Orion, which humans had gazed at for tens of thousands of years in essentially the same form, looked visibly different. The shoulder was faint. Something was wrong, or something extraordinary was happening. The explosion hypothesis spread instantly and understandably. After all, Betelgeuse was already known to be a star in its final stages. The last time a supernova was observed in or near our galaxy was in 1604, and that event, Kepler's supernova, was visible to the naked eye in daylight for weeks. If Betelgeuse were to explode, it would be the most spectacular astronomical event in recorded human history. It would outshine the full moon at its peak. It would cast shadows at night. It would be visible in broad daylight. Entire generations of scientists had dreamed of witnessing such an event, and for a brief, breathless stretch of weeks, it seemed like that moment had finally arrived. But as data accumulated, as the world's sharpest minds analyzed what the telescopes were actually showing, a completely different and frankly even more fascinating explanation emerged. Betelgeuse had not begun to collapse. What it had done was, in some ways, even more remarkable. In a fit of almost incomprehensible stellar violence, Betelgeuse had blown a chunk of itself off its own surface. Scientists call this a surface mass ejection, and while we have surface mass ejections from our own sun in the form of solar flares and coronal mass ejections, what Betelgeuse did was to solar activity what a nuclear weapon is to a kitchen match. A titanic bubble of superheated plasma containing mass that dwarfs our moon many times over was hurled outward from the star's surface at extraordinary speed. As this enormous blob of stellar material moved away from the heat of the star, it began to cool, and as it cooled, it condensed, transforming from a cloud of roiling plasma into a vast, dark, opaque shroud of cosmic dust and soot. This self-generated cloud positioned itself between Betelgeuse and Earth acting as a celestial blindfold, blocking enormous amounts of the star's light from reaching us. We were not seeing the star dim because it was shutting down internally. We were seeing it dim because it had literally thrown part of itself into our line of sight. The veil was made of Betelgeuse. The star had created its own eclipse. This discovery was simultaneously a relief and a revelation. A relief because it meant the supernova was not imminent, and a revelation because it demonstrated that these dying red supergiants are capable of violence and instability at a scale that had never been directly observed before. Betelgeuse was not quietly preparing to die. It was raging, it was turbulent, it was throwing material off its surface in eruptions so powerful they redefine our understanding of what a star can do to itself in its final evolutionary stages. But even this discovery left a question unanswered, because it was not the first strange behavior Betelgeuse had ever displayed. For decades before the Great Dimming, astronomers had noted a second, subtler rhythm in the star's behavior, a slow, steady pulse that repeated on a roughly 6-year cycle, a rhythm that did not fit neatly into any model of how a lone red supergiant should behave. Betelgeuse was already known to have a shorter pulsation cycle of about 400 days tied to its internal convective processes, massive bubbles of plasma rising and falling like a boiling pot of soup scaled up to planetary dimensions. But this 6-year rhythm was different. It was too regular, too persistent, too precisely timed to be random stellar noise. And slowly, through years of painstaking data analysis using observations from the Hubble Space Telescope and some of the most powerful ground-based observatories on the planet, astronomers arrived at a conclusion that genuinely stunned the scientific community. Betelgeuse is not alone. There is another star, hidden in the glare and the complexity of the system, tucked so close that it had evaded detection for centuries of observation. There exists a companion star. Scientists have named it Saraph, and its orbit is not a distant, gentle ellipse. It circles Betelgeuse at close range, so close that during each orbit it actually plows directly through the outermost layers of the supergiant's extended atmosphere, the thin, wispy envelope of gas and dust that extends far beyond the visible surface of the star. This interaction creates disruption on a massive scale. Think of a speedboat cutting through a perfectly calm lake, and then imagine the speedboat is itself a star, and the lake is the outer shell of one of the largest known objects in the galaxy. The wake created by this orbital intrusion ripples across the surface of Betelgeuse, disturbing its already unstable outer layers, potentially contributing to the convective chaos that drives those massive surface mass ejections. The discovery of Saraph fundamentally changes how we understand Betelgeuse, because it means this is not a solo performance. The instability we observe, the dimming events, the eruptions, the unpredictable surface behavior may all be partially orchestrated by a hidden gravitational partner that has been quietly pulling strings for millions of years. Betelgeuse is not just a dying star. It is a dying star in a complicated relationship, and that relationship may be directly shaping how it dies. This brings us, finally, to the James Webb Space Telescope, and to the claims that have been sweeping across social media with the kind of velocity that outpaces accuracy by several light years. The viral headlines suggesting that Webb has captured Betelgeuse in the act of exploding are, to be frank, wrong. Not slightly wrong, fundamentally wrong, and understanding why they are wrong actually reveals something about Webb that is far more impressive than simply pointing a telescope at a bright object and watching it blow up. Betelgeuse poses a unique problem for the James Webb Space Telescope, because Webb is one of the most sensitive astronomical instruments ever built, designed to detect the faintest possible signals from some of the most distant and dim objects in the observable universe, objects that emit almost no light at all. Betelgeuse, by contrast, is one of the brightest stars in Earth's night sky. Pointing Webb's extraordinarily sensitive infrared detectors directly at Betelgeuse for any meaningful period of time would be the equivalent of using the world's most delicate and precisely calibrated scientific photometer to look directly into the sun. The detectors would be overwhelmed entirely, the data would be saturated, useless, corrupted. You would learn nothing about Betelgeuse and potentially damage instruments that took decades and billions of dollars to develop. So Webb is not staring at Betelgeuse, but what it is doing is, in many ways, a more profound and strategically brilliant approach to understanding what Betelgeuse is becoming. Webb's true superpower in this context is its infrared vision, the ability to see through the thick clouds of gas and dust that surround dying stars, the very material that makes them so difficult to observe during their most critical final stages. In the period leading up to a supernova, red supergiants envelop themselves in cocoons of their own ejected material. They become shrouded. From the outside, they look dim, faint, or even invisible in optical light. But in infrared, the emission signatures of that material glow clearly, and Webb can read those signatures like a detailed map of a star's internal processes and timeline. Just recently, Webb turned this capability toward another red supergiant in a distant galaxy, a star already deep into its terminal phase, so heavily cloaked in its own expelled dust that other telescopes could barely register it at all. Webb saw through the shroud completely. It captured the star's temperature profile, the chemistry of its ejected layers, the rate at which it was losing mass, and the structural signatures that pointed unmistakably to a star on the razor's edge of detonation. Webb was building a detailed portrait of stellar death in progress, and crucially, it was doing so before the explosion, which is something that had never been achieved with such clarity before. This is the key to Webb's role in the Betelgeuse story. It is not capturing Betelgeuse exploding. It is studying other red supergiants in their final stages, building a comprehensive and increasingly detailed model of what the hours, the days, the years before a supernova actually look like from the inside, what physical signatures appear, what chemical changes occur, what emission patterns precede the collapse. It is constructing, star by star, and observation by observation, the definitive playbook for how a red supergiant ends its life. And Betelgeuse, when that moment finally comes, will be the most comprehensively anticipated stellar death in the history of astronomy, because Webb and every other telescope currently operating will know exactly what to look for and exactly how to interpret every signal. There is something both humbling and deeply moving about this picture when you sit with it. Betelgeuse is 700 light years away from Earth. The light you see when you look at Orion's shoulder tonight left that star 700 years ago. You are not seeing Betelgeuse as it is right now. You are seeing it as it was in the early 1300s, long before the printing press, long before Columbus, long before any of the events that shaped the world you were born into. For all we know, Betelgeuse has already exploded. The light from that explosion may be racing toward us right now at 300,000 kilometers per second, and we won't see it until it arrives, possibly decades from now, possibly centuries. That is an extraordinary thing to hold in your mind. A star may have already died, and we exist in the gap between the event and the knowledge of it. And when that light does arrive, when that wave of photons generated by the collapse of an entire stellar core reaches Earth and floods our night sky, we will have Webb's observations to help us decode every detail of what we are seeing in real time. That is the revolution Webb represents in this story. Not a single dramatic image of an explosion. A systematic, methodical, years-long campaign of observation that means we will understand Betelgeuse's death more completely than any stellar death that has come before it. Meanwhile, the star itself continues its turbulent, restless countdown. Its surface churns with convective cells so enormous that a single bubble of rising plasma on the surface of Betelgeuse would swallow the entire Earth. Its atmosphere extends so far into space that if Betelgeuse replaced our sun, its outermost wisps would brush the orbit of Saturn. It pulses and heaves and ejects material and wobbles under the gravitational influence of its companion, and deep in its core, the nuclear chain that has powered it for 10 million years approaches its irreversible final link. The iron deadline is coming, maybe tomorrow in cosmic terms, maybe in 100,000 years by our calendar. But the physics allows no other conclusion. When the iron accumulates beyond the critical threshold, the collapse will begin, and it will complete itself in less than a second. Everything that follows, the outward explosion, the shock wave propagating through 700 light years of space, the months of brilliant illumination in Earth's night sky, all of that happens after the core has already gone. The star will be destroyed before the light from its destruction reaches its own surface. There is a version of this story that is easy to tell, and it is the version the viral headlines prefer. A famous star is exploding, history is being made, science has captured the moment. That version is exciting, and it is built for clicks. But the version that is actually true is something richer and stranger, and if you have the patience for it, far more rewarding. A red supergiant 700 times the width of our sun is living out its final centuries in increasingly dramatic fashion, shedding mass in eruptions of planetary scale, harboring a hidden orbital companion that disturbs its surface and deepens its instability, and pulsing with the kind of chaotic energy that only a star staring down its own inevitable end can produce. And humanity, for the first time ever, has instruments sophisticated enough to read the signals, parse the chemistry, see through the dust, and prepare in advance for the moment when the universe puts on its most spectacular show. What Webb is giving us is not a photograph of an explosion. It is something quieter and more profound. It is understanding. It is the ability to look at a dying star and know not just that it is dying, but how and why, and what the universe will look like in the moments after it does. The next time you step outside on a winter night and find Orion in the sky, take a moment to look at the upper left star of the constellation, the orange one, the shoulder of the hunter. It is burning 700 years in the past as you look at it. It is on the edge of something that will reset everything we think we know about stellar explosions. And somewhere, right now, in a control room surrounded by monitors displaying data from the most advanced telescope in human history, someone is watching the stars nearest to it in age and size and composition and learning everything they can about what is coming. They will not miss it. We will not miss it. The universe does not announce its most dramatic events in advance, but for the first time, we are close to being ready. And that, far more than any misleading headline, is the genuinely terrifying and genuinely magnificent truth of what is happening in the sky above you tonight.